Hi guys, welcome to our revision lesson for the grade 12 trigonometry. Basically what we're going to be doing is we're going to revise your grade 11 trig, which you desperately need for grade 12, and we're just going to remind you how the Cartesian plane works. So if we just come here. Alright, so if we have a look at our Cartesian plane, we're starting over there at the 0-degree line, and then we always move in that direction on the Cartesian plane, which is the positive direction. And then what we need to always determine is the correct quadrant that we need to be in. So you'll see on the diagram that we've got a C there, an A, S, and T, and what it tells us is which trig ratio is positive in which quadrants. Okay, so if you have a look here, C, A, S, T, and some teachers call it the cast diagram. Other teachers have a little clever rhyme that you can use to remember it. And if you go from quadrant 1 into quadrant 2, you can say, all science teachers are crazy. And that's a little joke to just remember how we are going. So in quadrant 1 over there, all our trig ratios are positive. In quadrant 2, only sine is positive, which means that cos and tan will be negative in quadrant 2. And then in quadrant 3, we've got T for tan, which means that only tan is positive in quadrant 3. And in quadrant 4, we've got C for cos. So only cos is positive in quadrant 4. And that means that sine and tan will be negative in quadrant 4. So we just quickly run through it again. In quadrant 1, all the trig ratios are positive. In quadrant 2, only sine is positive. In quadrant 3, only tan is positive. And in quadrant 4, only cos is positive. And like I've said before, if you know which quadrant you are in when doing your trig, you will be fine. Okay, so if we have a look at this example, we've got sine A is equal to 3 over 5. Now, we must remember that our right angle triangles that we're going to be working in, we've always got x in line with our x-axis, y parallel to the y-axis, and then r, which is the radius of our right angle triangle. So all of our trig ratios, we need to learn them in terms of x, y, and r. So sine is always y over r. Cos is going to be x over r. And tan would be y over x. So just something to remember, and you really do need to remember that, because otherwise you are not going to be able to substitute. And that's actually what we are trying to do, is we want to substitute from our right angle triangles and then solve from there. Let's get rid of this quickly. Okay, so these are just two examples, and if we have a look over here, you will see that A is the element between 90 and 270. So if we go back to the first one over here, between 90 and 270. So we need to choose the correct quadrant for that information. So let's go back there, and it says sine is 3 over 5. And you'll notice that sine here is positive. So that means that we would need to be drawing in this quadrant where sine is positive. So there's our diagram for the first one. And you'll see that we've drawn our right angle triangle in quadrant 2, which is the correct one. We're either in quadrant 2 or 3, but sine is positive. And out of quadrant 2 and 3, we know that sine is positive in only quadrant 2. So therefore, we draw our right angle triangle in quadrant 2. And how you do it is you always start at the origin and you draw away from the origin onto the x-axis at 90 degrees. Then you go and put in your information. Firstly, you've got to show your angle over there. always show the angle. And you will notice that we've drawn from the 0-degree line all the way into quadrant 2, which makes our angle A obtuse. At this point, we now fill in our triangle. And we know that sine is y over r. So y over r. What we now need to find is x. And how we would find x is we would use Pythagoras. So x squared would be the radius squared minus y squared in this example. So it would be, the radius squared is 5 squared, which is 25. And then we'd subtract 3 squared, which is 9. And we would land up with 16. But that is for x squared. We are looking for x. So to find x, we'd have to take the square root. And we would land up with x is 4. And then you go and put it in on your right angle triangle. At this point, it's a good idea to show you how this would be marked. So the first thing that they would do is they would say, okay, correct. You substituted your 3 and 5 correctly. You calculated 4 correctly, and you're in the correct quadrant. So you'd probably get about 4 marks for this. And the other thing is they don't tell you to draw this, but they award marks for it. So a neat little exam tip is always draw your Cartesian plane because you always get marks for it. The other reason we draw it is how are you going to know how to substitute if you don't have your diagram? So it's very important that you substitute. So let's go through it again. We're in quadrant 2 because sine is positive. We show our angle from the 0-degree line all the way onto the radius. We then substitute our values in. So we've got over here, we've got sine is 3 over 5, which is y over r. We were then missing x. So to find x, we use Pythagoras like we did over here. So you have to have Pythagoras. And then you just substitute the values that you've got into Pythagoras. And then at this stage, we must remember that to find x, we would have to square root both sides of that equation. And then we take that value over there and we sub in to x over there. And now our triangle is complete. At this point, they could ask us anything and we would be able to solve it. Let's just clear all of this away. Let's just quickly fix this diagram. And A. Okay, that's our Cartesian plan. And now we look at the next set of questions. So the first one says 2 cos A minus 1. What that means is 2 times cos A. You can put that in brackets. Minus 1. So if we go back to our diagram, we need to find the value of cos A off this diagram. So cos A over here is x over r, which means that our cos is going to be negative 4 over 5. And the reason why it's negative is we have our triangle in the second quadrant, where cos is negative. Cos is always negative in the second quadrant. So our calculation here would be 2 times negative 4 over 5 minus 1, which you then just plug into your calculator and solve from there. How they would mark it is they would mark the substitution. So you would get a mark there, and then whatever your solution is over there, you would then receive another mark. So the important thing is that you must show your substitution. That's the important thing. All right. All right, then our next one at number 2, we've got sine A divided by tan A. Now we've already got sine A. Sine A is 3/5. Divided by tan, we know is going to be negative. Now if we go back to our one over here, we need to find the value of tan A. We know it's going to be negative because tan is always negative in quadrant 2. But tan is y/x, which means that we are going to say y/x. So we know it's negative 3/4. Which then means we're going to say 3/5 times, remember the tip in times, negative 4/3. Now 3's will end up cancelling and we will be left with negative 4/5. And you should remember that that was actually cos A. So what we've learned from here is that sine A divided by tan A will give us cos A. And you should remember your quotient identity from last year, which means that sine over cos equals tan. And then we can have any variations from there, which we did over here. All right, let's just erase all of this quickly. All right, so the basics that we need to do on the Cartesian plane, and how we actually know we're on the Cartesian plane, is they gave us a restriction. They said that A was between 90 and 270. And the minute you've got a restriction, then you know that you have to draw a right angle triangle on the Cartesian plane. All right, number 3, we've got 4 sine A plus 3 cos A. So what that means is 4 times sine A plus 3 times cos A. And we've already got those values. So we know that sine was 3/5 and it was positive. And then we've got 3/1 times, and we know that cos was negative 4/5. And you just multiply out now. So now we're going to get 4 times 3 is 12, and 1 times 5 is 5, minus 12/5, which means that our answer for that one is 0. So again, if we have a look at our substitutions, you will get a mark over there, and you'll get a mark over there, and 1 over there. So this one would probably be worth about 3 marks. You can't get all 3 if you don't show your substitution. And sometimes with a question like this in an exam, they would say without the use of a calculator. So there's only one way to do it. You've actually got to show every single step as you are going through, every single step, and then they will award you full marks for the sum. It often depends on the examiner. It depends on what instructions the examiner gives to the marker. Sometimes they say answer only, award full marks. Sometimes they say answer only, 1 mark. So we never know who sets our papers, and we don't know what the instructions are. So we don't take chances. We show all of our steps all the time, and we ensure that we are doing what we are meant to be doing. All right, the next question over here, we've got 5 tan A divided by 2 cos A. So that means that we've got 5 times tan A divided by 2 times cos A. So if we have a look here again, you'll see there's nothing there between the 5 and the tan. That implies that we are multiplying. And likewise, between the 2 and the cos there, right over here, you will see that there's no sign, and that implies that we're going to be multiplying. So if we come back here, 5/1 times, if we go back up here, we had tan was negative 3/4, so negative 3/4. Now I've shown that as a substitution, Then we're going to have 2 over 1 times, and then we had tan was negative 4 over 5. So where does this 3 over 4 and this 4 over 5 come from? It comes from here. It comes from our Cartesian plane. So we worked out that tan was x over r, which meant x over r, and our 3 was the y value. So we know that tan was y over x. And these are things that you need to know off by heart. So you need to know that x over r is the cos ratio, and you need to know that y over x is the tan ratio. And now we complete our steps. So 5 times negative 3 is negative 15 over 4. Divide by 2 times negative 4 is negative 8 over 5. And then from our algebra, we should remember that the divide changes to time, and then we invert our fraction. So 5 over negative 8. And then you plug that straight into your calculator if you're allowed. If you're not allowed, check what can cancel. So 15 times 5 should give us a value. So 2 15s are 30. So we should get 75 over negative 32. And from here, we must see if we can simplify. The instruction in maths is always to simplify. Even if they don't say it, we have to write our values that we get in their simplest forms. But this isn't where the issue lies in this sum. The issue in this sum over here is that you were able to recognize this part here. Do you recognize what you need to do there? And the most important step is actually that one. Did you substitute correctly from your diagram? And then after that, it's what we would call basic arithmetic. Can you multiply? Can you simplify? But it doesn't matter if you can actually do that if you can't do that step over there, which is to substitute correctly from your Cartesian plane. So always remember to show every single step, particularly if you're not allowed a calculator. All right, then our last question on that particular Cartesian plane is you will see that they actually want angle A. So that's different. The other questions just required a substitution into whatever we had. This one's different. They don't want a substitution necessarily. They want us to find the size of angle A. So let's go back to the original diagram. Here is angle A, from the 0 line past 90 degrees into quadrant 2. So what we are saying is that our angle A lies between 0 and 180, which means that angle A is obtuse. That means larger than 90 degrees, but smaller than 180 degrees. So we're going to have to use one of our trig ratios to find angle A. My suggestion is you always use the given one, because you know that's correct. You may have made a mistake here with Pythagoras, and then how are you going to actually get angle A out if you are using the wrong ratio? And try and stick with a positive ratio like we've got here. Right, so we now need to find angle A. We should remember that to find angles in trig, it is the inverse of our trig ratio with one of them that they have given us. So if we go onto our calculators now, we would switch our calculators on. We would press shift, we would press sign, then our fraction button, 3 over 5, close the bracket and equals. And we see that we get 36.87 degrees. Now, if you go back to the diagram, can you see that that angle does not actually fit our diagram over here? Because 36 degrees is in quadrant 1, but we're actually in quadrant 2. And if you remember from your reduction formula, quadrant 2 is a 180 minus your acute angle quadrant. So if we come back over here, we say, therefore, angle A is 180 degrees minus 36.87 degrees. And always show your degree sign. So therefore, angle A, and now we calculate it, 180 on your calculator minus the 36.87. And we see that we get 143.13 degrees. Now, take that angle and check your diagram. Does 143 degrees match the quadrant that our triangle is in? So is quadrant 2 bigger than 90 and smaller than 180? Because remember, we've got 143.13 degrees. And we will see that, yes, it does match our diagram. A common mistake that people make is they stop right over here. Right here. That's where they stop. They don't go back to the diagram and check, does my angle match my diagram? So we've got 36.87 degrees, but our angle A is not 36.87 degrees. If we go back to our diagram, we will see that angle A takes us all the way here into quadrant 2. So it's got to be larger than 90, but smaller than 180. So what we say about that 36-degree story is that it equals a reference angle. And that concept is very important in trig, a reference angle. It means a positive acute angle in quadrant 1. And we are always looking for a positive reference angle. Why? Reduction formula. All of our reduction formulas work with the reference angle being positive and acute. So basically, we must always remember, which quadrant are we in? We were in quadrant 2. And quadrant 2 is always a 180 minus our reference angle. So if we go back here, and we see there, we know that that is our reference angle. It's positive and it is acute. And then we simply apply our reduction formula over there. And then we land up with the correct angle according to our diagram. So if we have a look over here again, and we look all the way, firstly at number 1, they just want ratios substituted. Number 2, they want ratios substituted. From where? The Cartesian plane. Number 3, they want ratios. Number 4, they want ratios. But number 5 is different to the previous 4. They have that sign, which means they want angle A. And an angle is always in degrees. A ratio is always a fraction. So you must be very clear. Are you substituting a ratio, or are you trying to find the size of an angle? And the angle's got a dead giveaway. It's got the little roof of a house, you could say, if you wanted to. All right, let's look at the next one. We've got 7 theta plus 2 equals 0. That doesn't help us much because we could be dealing with a trig equation here. We don't know, so we need more information. Now they tell us that theta lies between 180 degrees and 360 degrees. That's the giveaway that you have to work on the Cartesian plane. They will give you a restriction. So we've got our restriction, and that tells us automatically that we need to draw our Cartesian plane, even if they have not told us to draw the Cartesian plane. Now we come back to our ratio that was given to us. 7 cos theta plus 2 equals 0. What we need is cos theta by itself. So we take the 2 across the equal sign by changing the sign, and then we divide by the coefficient of cos theta. And what that means is you simply divide by whatever is standing in front of the cos. And we need to remember that cos is x over r. Now, you'll see over here that cos is negative, and it lies between 180 and 360. Now, we know that cos is positive in quadrant 4. We're either working in quadrant 3 or we are working in quadrant 4. We can't work in both at the same time. So we need to look at our ratio again. We got a negative out. So that means that we have to be in quadrant 3, because out of quadrant 3 and quadrant 4, cos is only negative in quadrant 3. So again, you draw your right angle by starting with the radius. You draw away from the origin and then onto the x-axis at 90 degrees. And it's always like that. So away from the origin, onto the x-axis at 90 degrees. And you should remember that from your grade 10 and grade 11 trig. That you should remember. But sometimes we just need a little bit of reminding. Okay, so our x is going to be 2, which is over there. And then r is 7, which we will put in there. Now, some of you might be saying, but why haven't you written negative 2? Well, you can write negative 2 if you want to. But basically what our ratio is saying is we are working with distances. So x is 2 units long. R is 7 units long. And when we are showing distances on the Cartesian plane, we always show them as positives. How we get our negatives out is if we apply the cast diagram. All right, now we don't know y, so that we need to calculate. So according to our diagram, we would say that y squared is going to be our radius squared minus x squared. And that is from Pythagoras. So we're going to say 7 squared minus 2 squared. So we are looking at 49 minus 4. So therefore y squared is going to be 45. But we don't want y squared. We want y. So therefore y is root 45. And you could simplify that into simplified third form. So we should remember that 45 is 9 times 5. So basically we are saying 3 root 5. And they like us to work in simplified third form. So this over here is actually quite important. Always write in simplified third form. And especially if you don't have a calculator, they might ask you to work in simplified third form. All right, let's just tidy our diagram up here. Get rid of all of this. Okay, so basically with our right angle triangles, I think we're all happy that we have to use Pythagoras because our ratios only give us 2 of the 3 ratios that we are looking for. So we're either looking for x, or we're looking for y, or we are looking for r. And we need to be very clear which one we are looking for. So we should remember that we got 3 times root 5 for y. And now if you quickly were to have a look over there, you could say the following. Cos theta is negative 2 over 7. Tan theta, which is y over x, would be positive 3 root 5 over 2, because tan is positive in quadrant 3. And then our sine would be negative, and sine is always y over r. So negative 3 root 5 over 7. So now we've got our important ratios. We've got cos, we've got tan, and we have sine. And now from here, we can substitute anywhere. So let's see what questions await us. The first question we've got is sine squared theta plus cos squared theta. Okay, so what that means is the following. Sine theta times sine theta plus cos theta times cos theta. And you should remember this from last year. That is your squares identity. So we know that the answer is 1. But we have to show the substitution to get us to the 1. All right, so let's go back, and you will see that sine was negative 3 times root 5 over 7. So we are looking at negative 3 root 5 over 7 times negative 3 root 5 over 7. Remember your brackets, and then plus, and cos we had negative 2 over 7 times negative 2 over 7. Just like that. And now you simplify from here. So we should land up with the following. Negative 3 times negative 3 is positive 9, and root 5 times root 5 is 5. So 9 times root 5 is 45 over, and then we're going to get 49. 7 times 7 is 49. Plus, negative 2 times negative 2 is 4 over 49. So 45 and 4 is 49 over 49, which is 1. And there we go. We have proven our squares identity. So whenever we see sine squared theta plus cos squared theta, we know that the answer is 1. But we have to prove it with all of these steps over here. We have to show all of our steps to show that we understand how to substitute off the Cartesian plane. And a lot of it is not necessarily difficult, it's just long. And because there's so many steps involved and you've got to reason so many things out, it is very easy to make simple mistakes. Very easy. So always make sure that we are substituting correctly. Okay, now if we look at the next one, we've got cos theta divide by negative 3 tan theta. So you can rewrite that as cos theta divide by negative tan theta. Put that in brackets because it's a fraction by itself. Plus, and open brackets, 2 times sine theta. So now we need to go back to the original diagram, and we go and look for cos, which is negative 2 over 7. Tan, we've got 3 root 5 over 2, and then sine, we've got negative 3 root 5 over 7. So negative 2 over 7 divide by, oops, and over here we had negative 3. So negative 3 times, and we go back, 3 root 5 over 2. Close the brackets, plus 2 times, and we have negative 3 root 5 over, and just go back and have a look, 7. So that step's actually very important. You have to make sure that you have substituted correctly, because it doesn't matter how well you work after that. If your substitution is not right, the rest is not right. Okay, so now we've got negative 2 over 7 divide by. So we're going to get negative 9 root 5 over 2. And here we're going to get negative 6 root 5 over 7. And then over here, we must remember the tip and time story. So negative 2 over 7 times 2 over 9 root 5. Minus 6 root 5 over 7. And from there, we would actually just simply show on our calculator, if you're allowed a calculator, you'd simply type it in. But the most important step is that one. Did you show the correct substitution for cos? Did you show the correct substitution for tan? And did you show the correct substitution for sine? That's the first thing the marker is going to look for. And then after that, it's simply a matter of typing things in correctly onto your calculator or applying the correct arithmetic. So you will notice that I often just do that for the answer, because it's not the answer that's important. It's, did you get the correct substitution? Did you show that cos was negative? Did you show that tan was positive? Did you show that sine was negative? Did you substitute correctly from your Cartesian plane? That's where most of the marks are awarded, and the answer might only get 1. So it doesn't matter what your answer is if your working was not correct. So we've got to make sure that our substitution is correct. Right, and then you'll see for the last question, it just says theta. So again, that's like our first example where they wanted angle A. They want angle theta. So we need to remember which quadrant we're in. And if we remember which quadrant we're in, we know exactly how to go and find it. I'll just quickly erase here. Okay, let's go back to our previous diagram. You will see that we are in quadrant 3. And what that means is we are looking for an angle that's larger than 180, but smaller than 270. That's what quadrant 3 means. And if we remember our reduction, quadrant 3 is a 180 plus our reference angle quadrant. Always 180 plus our reference angle. So now we require a positive ratio so that we can get out a positive reference angle, which means we're going to have to work with tan to help us. So now we say theta is equal to tan to the minus 1 of, let's quickly check again what tan was, 3 root 5 over 2. So you substitute in the ratio to get the angle out, but you have to press shift on your calculator. That will get you the minus 1 out that we see over there, and then you type your ratio in for tan. So we press shift on our calculator, open the fraction sign, and then we've got 3 root 5 over 2. And remember to close your bracket once you've substituted. And we see that we get 73,4 degrees. That is your positive reference angle. So let's quickly go back to our diagram, have a look there. We are in quadrant 3. There is no ways that 73 degrees is in quadrant 3. So how we get it out is we remember to apply our reduction formula, which is the 180 plus the reference angle in quadrant 3. So therefore, theta is 180 degrees. And remember, you have to show your degrees. If you don't show your degrees, you don't get marks. So therefore, theta is 253,4 degrees. Now let's have a look at that now. We've got 253,4 degrees. Let's go back to our Cartesian plane. There we go. Does 253,4 degrees fit in quadrant 3? Remember we said we need an angle that's bigger than 180 and smaller than 270 for quadrant 3. 253,4 satisfies that restriction. We are definitely within our range between 180 and 270 degrees. So we know that we are probably correct with our Cartesian plane. And that's that example complete. All right, and you'll see here that it says it is very important that you recognize where to work on the Cartesian plane. And in grade 12, we're going to do something called double angles and compound angles. And these need to be reflected on their own Cartesian planes. So we need to be very careful how we work on the Cartesian plane. We need to be able to recognize when to work on the Cartesian plane. That's the other thing we must always be very careful of. And that is our revision complete for the Cartesian plane. Okay, so now we can move on to our reduction formula. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, you'll notice in quadrant 1 that we've got the most reduction formula. The first one simply says A. That is a positive reference angle. We know how to work with reference angle. The second one says 360 plus A. So if we were to draw in a radius, there, and then from our zero line onto the radius, that is angle A. So made between 0 degrees and 90 degrees. That is angle A. Now if we look at this reduction formula again, it says 360 plus A. So that means from this line, we have to go all the way around by 360 degrees, which takes us back to quadrant 1. So whenever you've got a 360 plus A, you are in quadrant 1 every single time. Right, our next one says A minus 360. The negative direction of the Cartesian plane is down. So A minus 360 means we must move from our line that angle A made, the radius, and we must subtract 360 degrees, which takes us back to angle A. So A minus 360 is always quadrant 1, every single time. Let's just erase this quickly. All right, now you'll see the next one is 90 minus A. 90 minus A means we're always going to be working from here in that direction. And you notice here we've got a plus A, which means we're moving in that direction. Now, whenever we have 90 degrees, we talk about something called the Coco rule. The Coco rule is informal maths English for changing the trig ratio to the complement of the co-ratio. So we simply say Coco rule. And what Coco rule means, and you can only use Coco rule within 90 degrees. So you must be on the lookout for this 90 degrees because it's always going to be the Coco rule. And how the Coco rule works is it says, if you have a cos, 90 plus or minus an angle, it changes to the sine of that angle, but it could be plus or minus, depending on what we've got. And likewise, if we had the sine of 90 plus or minus our reference angle, it will change to cos of that reference angle, but it could be plus or minus, depending on which quadrant you're in. So that Coco rule, you've got to be sharp because it sneaks up on you before you know it, and then you forget to change sine to cos, or we forget to change cos to sine. So how does it work? Step 1, if we have 90 minus A, like we've got over there, 90 minus A means we're always going to be in quadrant 1. And we know that all trig ratios are positive in quadrant 1. So if we had sine 90 plus A, sorry, not plus A, minus A. See, you've got to be pretty sharp about how you are doing this. Minus A. Let me show our reduction in brackets. The first thing we notice is we've got a 90. So that says Coco rule, which means that sine will change to cos of angle A. And it's positive because sine The original ratio is positive in quadrant 1. So therefore my cos is going to be positive in quadrant 1. If I had cos 90 minus A, same rules apply. I notice I've got a 90, which tells me Coco rule. So cos changes to sine. 90 minus A is quadrant 1, where cos is positive in quadrant 1 and reduces to simply sine A. So the 90 minus reference angle, that is very easy. It will change from sine to cos, but not be negative. It will always be positive because we're in quadrant 1. Right, let's erase this. All right, but the next part of our Coco rule is when we say 90 plus our reference angle. And when you've got 90 plus your reference angle, it takes you into quadrant 2, which is over here. 90 plus our reference angle is quadrant 2, right there. So if we had sine 90 degrees plus A, we see the 90, which means Coco rule, sine changes to cos. But now look at your original trig ratio. The original one is sine. We know that sine is positive in quadrant 2, so therefore it changes to positive cos A. And that should confuse some of you because you are used to seeing cos as a negative in quadrant 2. But what was our actual ratio? Our actual ratio was sine. And sine is always positive in quadrant 2. So therefore our cos is positive. If we had cos 90 plus A, we've got to apply the same logic. What do we know about cos in quadrant 2? We know that cos is negative in quadrant 2. We've got our 90, which tells us we're going to use Coco rule. So cos will change to sine. And then we will reduce to simply sine A. And that should confuse some of you because we are used to seeing sine A as positive in quadrant 2. But it is negative because our original ratio is negative in quadrant 2. So therefore it becomes negative in the solution. And as we move around the Cartesian plane, you will see quadrant 3, it's 180 plus our reference angle or our reference angle minus the 180. Okay, so let's quickly draw in a radius. If we drew from a 0 line there, that would give us A. So what this minus 180 is saying is A minus 180. It's saying we need to move 180 degrees away from our original ratio, which means this. So that whole angle there is A minus 180. In other words, anytime we say a reference angle, subtract 180, we land in quadrant 3 every single time. And these are little tricks that you learn and you just apply them every single time. Okay, if you look at quadrant 4, you'll see it's got negative A. Negative A meaning a negative reference angle. Remember, Cartesian plane, if you want to move in the negative direction, you have to move away from the 0 degree, but down. So there we go. From the 0 degree line, down. That is negative angle A. Now remember, if we had cos of negative A, it's going to be positive cos A, because in quadrant 4, cos is positive. If we had sine of negative A, it's going to give us negative sine A, because sine is negative in quadrant 4. And likewise, if we had tan of negative A, we're going to get negative tan A, because tan is always negative in quadrant 4. These are your main reduction formulae that we work with, and you've got to be very specific with them. Which trig ratio are you dealing with? Which quadrant are you in? and then determine, are you positive or negative? And then you can work from there. And at the bottom here, you'll see it says always know which quadrant you are in. Because if you're not sure which quadrant you're in, you do not know which ratio is negative and which one is positive. All right, here's an example. We've got cos 90 minus x. That's a rule to me. Then we've got sin 180 minus x. That is quadrant 2. Cos 180, that is not reduction. So now we need to remember our cos graph. Looks something like that. Cos of 180 is always negative 1. So we need to keep in the back of our minds what our original trig graphs look like, because we may have to substitute from there. And tan of negative x is quadrant 4. Then we've got cos 90 plus x. That, again, is Coco rule. Sin 270, well, that's not a reduction. That's asking us to remember our original trig one. That is 270 degrees over there. And sine of 270 is negative 1 every single time. And then something strange happens. You've got a 540 plus x. Don't allow them to freak you out here. All you do with big angles is you minus 360 degrees. That's all you do. And then you work from there. So if we say 540 and we subtract the 360, we land up with 180 degrees. So basically what we are saying here is we are saying tan 180 plus x, which is quadrant 3. Then over here, we've got minus 180 minus x. What we do here is we take the minus out, and it changes to 180 plus x. Now that is something that we do know how to work with. Okay, so basically when you get reduction formulae, they normally worth quite a few marks, like 6 or 7. And generally how they mark it is for each reduction that you make, they award you a mark. So you'll see that I did a lot of reasoning first. Which quadrant are we in? What is the value of this? How do we apply that? There's a lot of thinking that goes into reduction formula before you write your answers down. So we never rush reduction formula, never, because we are after marks and we need to make sure that we apply it correctly. Okay, so we come back to our first reduction here. So 90 minus x is quadrant 1, and we know that cos is going to reduce to sine in quadrant 1. Then we've got sine 180 minus x. We know that that's quadrant 2, where sine is positive, so it reduces to positive sine x. Then we've got cos of 180 degrees. From our cos graph on the Cartesian plane, we know that the value of cos 180 is negative 1. Then we've got tan of negative x. And we know that negative x is quadrant 4, which will make tan negative in quadrant 4. So far, you should have about 4 marks already. Then we've got cos 90 plus x. Now 90 plus x takes us into quadrant 2, where cos is negative, but it's 90, which means it's the Coco rule. So cos will change to sine. So we must remember that cos is negative in quadrant 2. And by changing to the Coco rule, we get negative sine x out. Sine 270 over there, we remember that it is negative 1 according to our sine diagram. The 540, we simply minus 360 from there to get to the 180 plus x, which changes to tan x in the next diagram. And here we're going to get, remember we took out the negative from here. We took the negative out there. So negative times a negative. What we're saying there is sine 180 plus x is negative sine x. But we took out a negative. So we're going to multiply by negative 1, which gives us positive sine x. And now all that we do is we cancel wherever we can. So if we have a look at the next step over here, let's see what we've got. Where does this sine squared x come from? It comes from sine times sine. That gets me to sine squared x. The tan x is negative 1 times negative tan x is tan x. Then we've got a negative times a negative will give me a positive sine x, and tan x, and then sine x from here, like we showed you just now. And now we say that sine and this sine cancels with sine squared x. Tan x cancels with tan x. So essentially what we have said is the same divide by the same, which always gives us 1. And generally these things simplify to incredibly small values. So if you're landing up with an answer that's big, then you probably know you've made a mistake. So always be very careful in the first step that you do for your reduction. That is incredibly important. If you make a mistake at this point here, your answer is irrelevant. It makes no difference. So we've got to make sure that we reduce correctly. And like I said before, you will notice that there is an incredible amount of thinking that goes from that step to the next step, to the next step, to the next one. You've got to do a lot of reasoning. And you've always got to be very sure, where are you on the Cartesian plane? And then you will know how to apply your reduction formulae. All right, now we look at our next example. We've got cos of negative x, quadrant 4, sine 90 plus x, well, that's Coco rule. Then we look at the bottom. We've got a binomial, there are 2 terms in the brackets, times another binomial. Now, generally, we would simply FOIL if we had a binomial times binomial. But this is trig, and we are looking at reduction formula. So we've got to be very careful what we do. Okay, so how do they approach this? Firstly, they've got cos of negative x. Negative x means quadrant 4, and cos is positive in quadrant 4. So there we go. We've got positive cos x. Now we've got 90 plus x. That's quadrant 2. And we know that sine is positive in quadrant 2. But because of the 90, it changes to cos. And it's simply cos x. It reduces to positive cos x. From our previous example, we should remember that sine of 270 is negative 1. And sine of 90, if we remember correctly, remember the sine graph goes up first, that is 90 degrees. And sine of 90 is positive 1. And that's where that positive 1 comes from. In the next step, we make as small as possible. We simplify. So cos x times cos x is cos squared x. And then you'll notice I swapped the order around there. I went from minus 1 plus sine x. I simply swapped them and said sine x minus 1. And then I left the sine x plus 1 as sine x plus 1. Now you should notice the following. You've got a difference of squares. And what the difference of squares means is you've got a binomial times a binomial. They are identical except one is negative and one is positive. And we should remember that it simplifies to that. There will be no middle term in our trinomial. It would have cancelled. And now you'll see I've written squares identity. So let's remind ourselves, what is the squares identity? The squares identity says the following, that sine squared x plus cos squared x is positive 1. Be very careful with this one. If you had a minus sign over here, then the squares identity does not apply. It only works with a plus sign. But what if I wanted just sine squared x? I would have to get rid of this cos squared x here. So I'd have to say 1 minus cos squared x. And if I wanted just cos squared x out of my original squares identity, I'd have to say 1 minus sine squared x. And that would get me just cos on its own. But the original squares identity is that. Sine squared x plus cos squared x is 1. These bottom two are variations of the squares identity. So if we go back to over here, I know that I can rewrite that in terms of cos. Remember here? So you will see that in the next step, we've written 1 minus cos squared x minus 1. So what's going to end up happening now is that positive 1 minus 1 cancels, and we are left with cos squared x over negative cos x, which leaves us with negative 1. Okay, a common mistake that people make at this step over here is they say the following. They say sine squared x minus 1 is cos squared x. But it is not the case. Remember that it would be 1 minus sine squared x is cos squared x. So always be very careful. Apply your reduction correctly, and especially with your identities. You've learned that you can mix your identities in with your reduction formula. All right, let's see what's up next. General solution. Oh, general solution is a headache for a lot of people. They're not sure how to apply it. So I've reduced it for you to 3 basic formulas. The first formula is your sine. Now, we need to understand what general solution means. So let's draw our original sine graph. We are used to drawing maybe up until this point, 360. Because the period of a sine graph is 360 degrees. That's what we are used to for sine. But what if I went to 720? I would have to draw another one. And if we carried on to infinity, it's going to keep doing that. Keep doing that. And all of these values here, all of them would have the same value. We would get positive 1. And all of these ones are going to give us the exact same value. It's going to give us negative 1. So what this diagram is actually telling us is that many different values of theta or x will give you the exact same answer for y. And at the bottom, many different values of theta over there would give you negative 1. So that means in general, you could say that there are infinitely many possibilities that would give you the exact same answer. And that is why it is called a general solution. So the general solution means that we're actually working in an equation. We're trying to solve for our angle theta or our angle x, but we want to be able to find all the possibilities that give us the exact same answer. And that is why we substitute into a formula called a general solution. General in maths meaning more than one possibility. We are used to our equations giving us 1 or 2 solutions. General solution says that there are many different possibilities. So for sine, there are 2 substitutions. The first one is that theta is just our reference angle plus k times the period of sine. And the period of sine is 360 degrees. And remember, our k is always an element of the real numbers. And you must put that in because they award you a mark for saying k is an element of the integers. The second sub you do for sine is this one over here, where you say 180 minus the reference angle plus k times 360, where k is an element of the integers. 360 again, because to draw one complete sine graph, you need 360 degrees. But let's look at our Cartesian plan. The first one simply said theta. The second one says 180 minus theta. So we're in quadrant 1 and 2. That shouldn't surprise us because sine is positive in quadrants 1 and 2. So that one works. Then the general solution for cos, we say theta is plus or minus the reference angle. Now, let's draw a different Cartesian plane for cos. Cos is positive over there, theta, and if we had negative theta, we would be in quadrant 4. So where they say plus and minus theta, what they're actually saying is there's quadrant 1, there's quadrant 4. So this one, even though it looks like it's one substitution we are making, that plus and minus sign gives us two possibilities for cos. And then you should notice over here that 180, that's different. The other ones were 360. 360 for each one. 180 is because for our tan graph, our original tan graph, remember we had an asymptote at 90 and we had an asymptote at 270. And that's what your tan graph looked like, remember? So to draw one complete tan graph, you only require 180 degrees. And therefore, the tan graph always has a period of 180 degrees. And that is why in our general solution over there, we have 180 degrees. But you will see that it's only the reference angle plus k times 180. Which means we can only be in quadrant 1. Because 180 for tan would be positive in quadrant 1, but negative in quadrant 2. And we're only looking for the quadrants where it's positive. Okay, let's go to some examples, because let's face it, we only understand when we're actually working with these things. So if we look at the first example, we've got sine x is 0.87. So the first thing we do is we find our positive reference angle, which will be sine to the minus 1 of 0.87. So we land up with the following. So again, on your calculator, you press shift, sine 0.87. Now you say equals, and we land up with 60.46 degrees. Now that is our reference angle. If we go back up a page, we will see that we've got to say the reference angle plus 360 and 180 minus the reference angle because we are busy with sine. So now we say, therefore, x is our reference angle plus k times 360, where k is the element of the integers. Or x is going to be 180 degrees minus 60.46 degrees, close your bracket, plus k times 360, where k is the element of the integers. And then you would simplify in your next step. You would say 180 minus the 60.46, and we land up with 119.54 degrees plus k times 360. And that k times 360 is simply saying that we can multiply many times into 360, and that is what gives us the general solution. All right, now if we summarize the sine one again, we go back. For sine, right over there, it said reference angle plus k times 360, and then 180 minus the reference angle plus k times 360. And that is always how you do it for sine. Every single time, that is how you would do it for sine. Let me just clean up here a bit. Okay, our next one, we've got cos, and we've got cos of 2x. Now that is a problem for us because in our first example, you will notice that we had x. In this example, we've got cos 2x, and that sometimes throws a spanner in the works for some people. So always be very clear. How big is my angle? Is it just x, or is it 2x, or is it something else? Because depending on what it is, we have to change our method for solving. Okay, so we've got cos 2x is equal to 0.54. Now what we do is we solve for 2x like a normal trig equation. So we have to find the inverse of the ratio, the 0.54. So we land up with 2x is equal to. Now on your calculator, you would press shift, then you would press cos and 0.54. Remember to close the bracket, press equals, and we get that 2x is 57,32 degrees. And that is our reference angle. And you will notice that we have left the 2x. We have not solved for x just yet. So let's go back. Here's our general solution. It says you need plus or minus the reference angle. So now we say the following. Therefore, 2x is equal to plus or minus the reference angle plus k times 360. And it's 360 because you need 360 degrees to draw one complete cos graph. And don't forget, you need to say cos is an element of the integers. Okay, at this stage, now we can solve for x. So what do we remember? When we're solving for our reference angle, we treat that as one angle, because where we will solve for it is in the general solution. So now, x is equal to plus or minus. Now what we do is we divide every single term by 2. So we'll say 2x divided by 2 is x. Then we have to divide our reference angle. So we had 57.32. Divide that by 2 is going to give us 28.66 degrees. Plus, and 360 divided by 2 is 180. And that is very important. A lot of people forget that when you're dividing in any type of equation, that you divide right through, from left to right. Every single term gets divided by whatever is standing in front of x. And we would then be done. So what we learned from that example is that we only solve for x by itself inside the general solution. We don't do it there. At that step, we are simply trying to find the reference angle. And it is the reference angle that gets substituted into the general solution. From there, we now try and solve for x. So the most common mistake that people make is they solve for x here when they are finding the reference angle. What we need to remember is that you sub the reference angle into the general solution first, and then we solve for x. And it is like that every single time. And in maths, there are very few things that are the same every single time. So this is a nice one to remember, that it is always the same in general solution. Step 1, you find your reference angle. Step 2, you substitute your reference angle into the general solution. And step 3, then you solve for your angle. So let's go through those steps again. We first find our general solution. Then we first find our reference angle. Then you substitute the reference angle into the general solution. Once you're in the general solution, then you can solve for x. All right, now if we look at the last one that we've got 3 tan x minus 1.4 equals 0. So that means 3 times tan x minus 1.4 is 0. We need to get tan x by itself. So the first thing we're going to do is we're going to say tan x is equal to get a negative out of the way, we'll have to add it to that side, and then we would have to divide by 3. So tan x, in this example, we'll simply say 1.4 divided by 3, and we get quite a long decimal place. So you might want to leave it as a fraction, 1.4 over 3. Now what we need to do is solve for x. So we say tan to the minus 1 of 1.4 over 3. And how we do that is we press shift on the calculator, then you press tan, and then your fraction button, 1.4 over 3. And remember to close the bracket, and we land up with 25.02 degrees. And that is our reference angle. Now if we go back to our reduction formulae, to find our reference angle for tan, we say it's the reference angle plus k times 180 degrees. So let's go back. Therefore, x is equal to our reference angle, which is 25.02 degrees, plus k times, remember, 180 for tan, and k is an element of the integers. And then we would be done. Remember, an arrow underneath an answer means that you are finished with that answer. Right, and that's us for today. Thank you so much for tuning in. Hope that it was worthwhile and hope that you learned a lot. Please join us again every time that we work on the Center for Learning. We are very excited to be giving extra maths lessons at the Center of Learning. So please join us again. Thank you. Bye.